Okay, let me have everyone's attention, please. Separable differential equations. Is everybody listening? Separable differential equations. So remember, when in the last Zoom lesson, I wrote some stuff. I'm going to share that. Since I closed that meeting, it's not part of this slide. Quickly. Yeah. I wrote here, I said 3 things we want to try to do. The first thing is to be able to verify that solutions are different, that some functions are solutions of differential equations, and that you were able to do, okay? The next thing was to be able to solve differential equations of the form dy by dx is equal to function of x. Are you listening? Dy by dx is equal to function of x. So basically, on one side, you have your first derivative. On the other side, you have a function of x. And that is more or less the application of integration that you learned weeks ago. All you have to do is, if dy by dx is a function of x, the function itself will be the integral of that other side. Am I making sense? Like y will be the integral of that function. That you've already done. And I believe that's what you are still practicing right now. Now, the next set of differential equation, I don't think Mr. Cheng is listening to me because I can see that he's still writing. The next set of problems is when you have a function of x and y. Okay, remember in the previous one, your dy by dx is equal to a function of x. So you integrate directly. Okay, but if you have a differential equation whereby dy by dx is on its own, but the other side is not a function of x, but a function of x and y, we can use different approaches. Okay, it's not just this approach of separable variable that needs to be used. We have different approaches based on some reasons, and I will tell you in a bit. So let me go back to current slide, which is this one. Now, I hope you are listening. So this leads us to, this is the first new thing to you in this topic. Every other thing so far is not new to you with your knowledge of differentiation and integration. Some differential equations that are of the form of dy by dx equals function of x and y can be solved by an approach called separable variable. In my university days where I learned this, or even my polytechnic days, we call it separable variable. In your textbook, you see separable differential equations. You can also just call it separable variable differential equation. It means differential equations that is, the variables can be separated, as the name implies. Are you listening? The variables, the two variables x and y can be separated. In summary, remember, on one side is dy by dx. On the other side is a function of x and y. Okay? That function of x and y that is implicit. Remember, we have learned implicit, right? Implicit is when x and y are mixed together. Okay? That implicit function can be factorized separately with one factor only function of x, the other factor only function of y. If you can do that, it is a separable differential equation. Listen again. On one side, you have your dy dx, okay? On the other side, you have a function of x and y, an implicit function of x and y. However, that implicit function of x and y can be separated into product of two functions, okay? Such that one part of it is a function of x, implicit function of x. One part of it is an implicit function of y. If you can do that, if you can separate the variable, that's where the name comes from. If you can separate the variables into x and y, but they are binded with multiplication, not addition now, then you are dealing with a separable differential equation. Now look at what I wrote. I said some differential equations of the form dy dx equals f of xy, which can be transformed into dy dx. Can you see? F of x, I shouldn't have used f of x again because I call this f of x already. So maybe I could call this h, g, and h. What's wrong? What's wrong with my pen? I was struggling with my pen. I don't know what's happening. So maybe we can call this G and H instead of X and Y. I have no idea what is happening to my pen. No, it's working. It's just, can I have yours? Which one are you talking about? This minute it will work, the next minute it will not. What's going on? Oh no. What about my hand? Okay, my hand works. Anyway, nobody cares about the pen if my hand works. Just like my hand can't write too big. Okay, I think it's back. Awake now. It was sleepy or maybe hungry and now just eating some food. No. So let's call it G of X, H of Y. Okay, I hope everybody understands why I changed that, because we don't want to assume it's that same F we are talking about. So once it can be transformed into these are separable differential equations. That is, differential equations where the variables can be separated, even though they appear to be implicit of X and Y. Okay, now I'll show you. Now this is how we solve this kind of problem. So I want everybody to listen, please. To solve such problem is very easy stuff. To solve such problem, okay, we say, so remember, initially we have dy dx equals f of x comma y. The next thing we're able to say, oh, dy dx is now the product of gx and hy. Okay, the next thing we would do is to change both sides, collect like terms, so to speak. That is, with this dy, hy will come, with that dx, the other will go, like that, like this. So it's going to be dy divided by hy. Can you see this? Is equal to gx dx. Can you see that? Then we integrate both sides. Then integral of dy hy is equal to integral of gx dx. And we integrate both sides and we solve it. That's it. Because it makes sense to integrate a function of y with respect to y, a function of x with respect to x. Is that not? So this is the idea of separable differential equations. So let me show you some example. Okay, let me show you something in the book first. Can everybody see the book?
Yeah, I can see it.
All right. Now, look at this. Look at this, for example. It's an implicit function of x and y, but it can be separated. Oh, no. Yeah. Can you see? But it can be separated. Okay. Now, this is like just a function of y. You see, one of them could just be 1, while the other is this. Can you see this? And this is also a function of x and y. So you can actually say, oh, x plus 2 is one function, and the other function is 1 over g of 3. 1 over y of 3. Okay, y raised to power 3. Okay. So once you are able to do this, then we can use separable variable. Look at the analogy of your book also is the same. It's not the same as what I just said, but it's the same. If you have this, then you can integrate both sides. Of course, when you integrate f of x here, you have to say dx. And the other side, once you put the integral here with dx, it's like a chain rule. They cancel out, then you have this. So it's similar to something I just said now. So let me play you this so we can save some time. Let me play you this. Please, you give thumbs up if you can hear the audio. I've just shared the audio of my computer. Let me increase the volume to maximum. And give me thumbs up if you can hear me. Yeah, the audio.
In the differential equations we solved in the previous section, the derivative dy by dx could always be written in terms of x. We now consider a more general class of differential equations called separable differential.
What do you say?
We can't see the window with the.
Oh. Oh. Sorry about that. How about now? Okay, great.
Yeah.
All right, let's do it again.
In the differential equations we solved in the previous section, the derivative dy by dx could always be written in terms of x. We now consider a more general class of differential equations called separable differential equations. A differential equation is separable if the derivative can be written as a product of a function of x and a function of y. We call them separable because we can separate the variables so that one side involves y only and the other side involves x only. We can then integrate each side with respect to x to find a general solution. In part A, dy by dx is xy. We want to separate the variables so that only y is on the left and only x is on the right. So, we divide both sides by y. We now integrate both sides with respect to x. Applying the chain rule, the integral on the left-hand side is now in terms of y only. We can now perform the integration on each side. On the left-hand side, the antiderivative of 1 over y with respect to y is ln of modulus y. On the right-hand side, the antiderivative of x with respect to x is a half x squared. We only need to add a constant of integration on one side. If possible, it is good to write the solution with y as the subject. Since the exponential function is 1 to 1, e to the left-hand side must equal e to the right-hand side. So, y is plus or minus the expression on the right-hand side.
Does everybody understand that? Because of the absolute value. Remember, exponential ln something is just that something. Law of logarithm. Okay? A raised to power logarithm of anything to base a is that something. Okay? So if absolute value of y is this function, then y is plus or minus the function because you don't know if it is positive or negative. All right?
Plus or minus e to the c is just a constant. Its sign.
We always put a constant, not at the top, but as a product of the function. So if you separate this, you are going to have exponential this times exponential c, right? Times exponential c. So that exponential c with the plus or minus becomes a new constant introduced. Okay? And that's because we don't put the c at the top as an exponent.
Sign is determined by an initial condition, which we do not have. We call this constant a. So,
what kind of solution is this?
General.
A general solution. Okay? Because depending on the initial condition, you can get the value of a. Then you can have a particular solution. Now let's look at the second one.
We are left with a general solution for y in terms of x. In part B, the expression for the derivative does not include x at all. However, the differential equation is still separable, as the derivative is still a function of y times a function of x. We want to separate the variables so that only y is on the left-hand side. So we multiply both sides by y squared. We now integrate both sides with respect to x. Applying the chain rule, The integral on the left-hand side is now in terms of y only. We can now perform the integration on each side. We only need to add a constant of integration on one side. We want to write the solution with y as the subject, so we multiply both sides by 3, then take the cube root of both sides.
Understood? Now, what you could also do to make life easier, if integrating dx to both sides is not convenient, is to just do what we do in integration by substitution, where we treat dy by dx as a fraction. So you can cross multiply. Okay, that might be easier for some of us. I'll show you what I mean. So taking the first question, for example, dy dx is equal to xy. If I treat dy dx as a fraction, then it actually means dy is equal to xy dx. Then I remove all the y and bring it here. Then I'm having dy over y equals x dx, isn't it? Then I can integrate both sides. Integral of dy over y is equal to integral of x dx. Then I can have my natural log, and I can have my x squared over 2 plus c, and the rest continues. Okay, and in the second problem, which is dy by dx is equal to 1 over y squared, it's very easy also. So that would be y squared dy is equal to just dx. Then I can integrate y squared dy and also integrate dx. Then I have my y cubed over 3 is equal to x plus c, and the rest continues. Okay, so if looking at cross multiply makes life easier for you, please go for it. If you understand the multiplying, integrating with respect to x and canceling like it is done in that example, go for it. Understand? All right. Okay, let's see if we can take one more example before you start working on it. I think I'll play you all the examples before we start doing practice, okay? So that if we do not have enough time, we don't have to delay each other, okay? So there are 3 examples from the book. I'll play the 3 examples for you, and you can always watch them again later. And I'll give you some work that you need to do, of course, which I must see, because I don't trust you guys to do it. Anyway, I do. This is not the second one. Let's see. I think it's this one. Yep. Give me thumbs up if you can hear this. Now, this is not just algebraic function. Now, this involves some exponential, I think, and logarithmic functions. Yeah.
In this example, we have a differential equation with an initial condition. Is the differential equation separable? The differential equation is separable because the derivative can be written as the product of a function of x and a function of y. We separate the variables by dividing both sides by e to the 2y. We now integrate both sides with respect to x.
Always y on the left. It is convenient that way. And put your plus c with x on the right. Okay?
Applying the chain rule, the integral on the left-hand side is now in terms of y only.
Did you see how exponential was transformed from here to here? You must recall your previous knowledge of integration. And did you see that this is linear, so it's easy to do? If this was cos squared, for example, you need to apply the trigonometric identity that we use. So you are recalling all your integral knowledge, please. Okay? You are building on these things now. Thank you.
We now perform the integration on each side, using the rule for integrating the composition of a function with a linear function. We add a constant of integration on one side. To make y the subject, we multiply both sides by -2. The constant of integration can just be left as c.
I hope you understand that, because it is a constant here. Even when you multiply by 2, it's still a constant, so we still call it c. Okay, can use small c, then capital C, it doesn't matter, just leave it as c. C is c.
We then take the natural logarithm of both sides, then divide both sides by -2. We substitute the initial condition and hence evaluate the constant of integration. We can now write down the particular solution to the differential equation with the given initial condition.
Does this make sense?
Mr. Daniel,
Yeah.
if you can just keep it as c, why did they change the constant to a in the previous example?
I think it varies with the person solving it. In the first one, it was changed. I will prefer it is changed, actually, because C could, if C was 4 on the first step, I don't want us to assume C is still 4 in the second step. You understand? I think we should have a consistent approach. Please change it. If you use C as a constant, change it to maybe A next, change it to B next, something like that. I would prefer it is changed. That's a good question. Does everybody understand this question? Okay, I would prefer it is changed, because this C here, is it here? Here is like double of this C here. But what they meant is that, oh, it is plus a constant, it is also plus a constant. So why not just call this C and call this another K, then, and so on like that. I would prefer it is changed. So good question. Any other questions? So we go to the last example. No? All right, the last example. Because some of us are trying to eat food. Someone is yawning because you want to eat food. She's in the dining area already, waiting for food.
For any worded question, it is important to read the information carefully.
Very important.
Take a few moments to identify the mathematical information it contains. You should notice the differential equation and also the initial population. The differential equation tells us that the rate of change of the quantity is proportional to the size of the quantity at any given time. This indicates exponential growth. In part A, we need to find the particular solution for P of t. The differential equation is separable. We separate the variables by dividing both sides by P.
Question, please. If this is dp dt equals to a function of one variable, who can tell me why we can't use the first method of direct integration? Again, this is dp dt is equal to 1/5p, just one variable. Why do we have to apply separable variable? Why not just integrate directly? Raise your hand, please, or just speak to the mic. Because this is not x and y, so it's probably difficult to see, but you need to understand why the x and y one is different from f of x1, then that tells you why this is a separable variable question. Anyone?
Oh, because it's dp over dt, not dt over dp. Is that why?
Exactly. You see, this is like your dy dx, right? Is equal to a function of y, not a function of x. In your x and y equation, when you say y is a function of x, y depends on x, isn't it? So we call y the dependent variable and x is the independent variable. So if you have your derivative is equal to function of the independent variable, like x, as a function of the denominator, okay? If this right-hand side contains your denominator, then that is direct integration. Are you with me? But it's like having dy dx is equal to function of y. then that is a separable variable question. Understand? Yes.
Can you make it like the first one where you just directly integrate if you just flip the signs? So like
we could do that. So what it's proposing is, what if we have it as dt over dp is equal to 5 over p? Yeah, we could do that, but let's listen to this first and compare the result later. Okay, we could do that.
Now integrate both sides with respect to t. Applying the chain rule, the integral on the left-hand side is now in terms of p only. We perform the integration on both sides, adding a constant of integration. Since the exponential function is 1 to 1, e to the left-hand side must equal e to the right-hand side. Since the population p cannot be negative, we can remove the modulus without needing a plus or minus. E to the c is just a constant, which we call a. So, we have a general solution for p in terms of t. We substitute the initial condition and find that a is 80. We now have a formula for the population p after t years. In part b, we substitute t equals 10 and evaluate the population using technology. It only makes sense to talk about a whole number of fish, so we round off to 591 salmon.
Does this make sense? So what Ethan is trying to say is this. He's looking at it from the angle of not applying the separable variable differential equation. But if you look at it closely, even the direct integration is more or less a separable variable differential equation. Let's see on this slide. This is the, I'm going to put the book version on this side. dp dt equals 1 over 5p. Then 1 over p dp dt is equal to 1 over 5. Can everybody see? Okay, then integral of 1 over p dp dt, then with respect to t, integral 1 over 5 with respect to t. So when this is gone, you have integral 1 over p dp equals integral 1 over 5p. I hope I'm not muting myself. Okay, I'm not. So this becomes the natural log of p, and this becomes 1 over 5. This is dt, sorry. And plus c, yes? So what else do we have? So p now will be exponential of all this, exponential of 1 over 5t plus c. So which is exponential. I'm trying to copy exactly what was done. But okay, so this is the step that was missing. And if this, now this is meant to be plus or minus. Okay, this is meant to be because of the absolute value, right? It's meant to be plus or minus, but because the population cannot be negative. Okay, this is since your population cannot be negative, then it's only the positive one. So p will be exponential 1 over 5t times a, where all this is a, and that is why you get a exponential t over 5. Are you with me? Now, that is the book version. What Ethan is trying to say the other time can also work. You have your dp dt equals 1 over 5p. So he's saying, now this is more or less p over 5. If you flip it, dt over dp will be equal to 5 over p. Now, this becomes your dependent variable, and this becomes your independent variable, like your x. So now you have it in the form of dy dx as a function of x. Understand? In that case, you can say, oh, t will be the direct integral of 5 over p dp. Yes? Now, if you notice, when you have dt dp as 5 over p, you are more or less also doing the variable, separable variable. How do I mean? Sorry, there's a dp here. When this goes away, like maybe when you cross multiply, p dt equals 5 dp. Then p will go on the other side. dt equals 5 dp divided by p. And when you integrate both sides, you have integral of dt equals to integral of 5 over p dp. Integral of dt is just t. Can you see that? So when you apply direct integration, it is the same as this separable variable also. But it's easier to do direct integration because we are used to this. So basically, t is equal to 5 with absolute value of natural log of, absolute value of, no, 5 ln absolute value of p plus c. Can you see that? I need everyone's attention and I need you to look at what I'm doing. So if I take c away, I get t minus c equals 5 ln absolute value of p. So I'm going to rearrange the side. Ln absolute value of p is equal to c over 5, okay, minus c over 5, which can be changed to another variable. So I can call this c over 5 minus a, for example, okay, or I call it k, okay, another constant, not as in carrying. So absolute value of p will be exponential c over 5 minus k. Okay, your population cannot be negative, so there's no need for the absolute value. Exponential t over 5, then exponential negative k, which could be changed to a. Can you see that? So we can say p is equal to a exponential t over 5. Can you see that we arrive at the same point? Mr. Cheng, does that answer your question? And the rest can follow. Okay, so there's no time. I'm going to indicate questions that I need you to try, and I need you to turn it in before tomorrow. Okay, let's do our class straight days unless somebody has a family event and you can't make it, so we can postpone. The idea is to have straight days so that we can all enjoy our vacation without seeing Mr. Daniel's face, right? Okay, so unless there is any objection, we can meet in the morning and quickly rush this for this week, and that's it. Except on Christmas Day, of course, like, so we can all enjoy Christmas morning. But if you want to come online on Christmas Day, I don't have an objection to that. I think, so some of us that love chemistry, we find this interesting. What is ethylene oxide? Well, I don't know what all this means. Looks like some hydrocarbon with some other complex stuff. So I will give you some problem that looks like that. Engineering problem, growth, Newton law of cooling. See, these are all differential equation problems, okay? We do application in physics, okay? I'll pick some questions and I need them done, okay? You don't have to turn it in tomorrow because, of course, you have other things to do apart from meeting me online. What I would want you to do is write it on a paper. Hopefully you have scanners, and scan it and send it across to me, okay? You send it across to me via email or something. You write it on a piece of paper, scan it. I will print it out here or maybe just grade it. If you are scanning, okay, let's do it this way. If you are scanning your solution, scan in JPEG form. Are you listening? Scan in picture form. It's easy for me to mark with my pen on the screen if I receive a picture format. Okay? Alternatively, oh, I think we should do that. I'm sorry. Alternatively, this is what I want you to do. Write in your notebook, okay? Take a picture, put it in a Microsoft Word, and email it to me. That's even easiest. That's the easiest form. Yes, Krista, you want to say something? I can't hear you. I can't hear what she's saying. Krista, I can't hear what you're saying because we need to go in 2 minutes. Okay, she's typing. Let's see what she said. I think my mic is not working. Yeah, we know that. But do you have any question? Do you understand what I said? Okay, so the reason I'm saying this is, remember how we did during the Zoom time? During the pandemic, sorry, this is still the Zoom time. During the lockdown period, you send your work through Microsoft Word. I check, and attach and send back to you. Remember that? Okay, so solve it in your notebook. Whatever I send to you, solve it in your notebook. Take a picture, but please send me a clear format. And those of you that are already using computer to write, like Mr. Cheng, for example, it's easy for him. Just copy those files and put it in a picture in a Microsoft Word document. Okay, so I don't have to open in a new application. I open your Word document. I can mark inside the work document and just attach to you. Just send your, put it with your name. Okay, just make sure the file name is your name and whatever. If there's any other instruction, I will send to you. Okay, make sure you send back within 2 days so you do not forget the idea. Okay, I will also make sure any question I'm giving you does not exceed 5 problems. Okay, I'll make sure it does not exceed 5. Something you can do within 1 hour. Just dedicate 1 hour to do it. Okay, over a period of 2 days maximum. If you want to send it back the same day, fine. Otherwise, take 2 days maximum, please. Okay, practice on your own. Ask me questions. Let's make sure we can do a lot of this before we go back to school. Hopefully, we can solve all the ODEs and also the McLaurin series before we go back to school. Okay, any questions? Nope. Okay, I'll see you guys tomorrow. Thank you for coming. Enjoy your vacation, even though you're stuck with me. Too bad, sorry. All right, bye.
Bye.